Okay. So this is the circuit that was assigned to me for presentation purpose. And here is the circuit of PTAT generator circuit, like voltage generator circuit by like the whole circuit name is PTAT voltage generator. So basically, it's a like proportion to absolute temperature circuit which actually generates the voltage. And the circuit uh, description. So basically, here is I here is one NMOS which name is M2 and another is M1. So both design parameter WIL ratio is different. So here the in M2 transistor, M2 NMOS transistor, my uh, WIL ratio is like multiply k times multiply of your of my M1 transistor. And what is basically VPTAT? Basically, VPTAT is your output. So uh, if I go through the circuit operation, so before that, uh, this circuit is actually want to operate in a sub-threshold region. So if we go through little bit device part, so what is sub-threshold region basically? So you have a MOSFET. So your MOSFET is working in normally like in digital. What do you know that your MOSFET is working after VGS greater than VTH. So in this scenario, your circuit will work at less than VTH. In digital domain, like if your circuit it is like your VGS is less than VTH, then circuit will be off, right? But in here your circuit will be operate, which actually we intentionally we want to operate this circuit or this circuit in a sub-threshold region. And how you get to achieve sub-threshold region? So basically the design parameter that I already told. So basically if your channel length is decreasing, if you are decreased your channel length, so that you can operate your circuit in sub-threshold region. So basically where your current is very less follow. And that current also dependent on the temperature variant. So our goal is that my circuit should be operating like want to like I want to operate my circuit in a in that region where it depends on the temperature. So basically my entire circuit is dependent on the temperature variant. If suppose my temperature is varies, so according to my VPTAT, so that I already told that my output varies. So basically it's generated voltage. So now go to the derivation part of my circuit. So basically here you can see in M1 that is VGS1. Here it is VGS1, and the VGS2 that is the gate and source voltage difference of my M2, that is my VGS2 here. So what is my VPTAT? So basically the voltage uh, generated by proportion to absolute temperature, that is my VGS1, that this voltage minus VGS2, this voltage. So and what is I bias? Basically I bias flow through this M2 transistor and M1 transistor. So entirely if I told about that my I bias current equal to IDM2 or IDM1. So both are same. So for in IDM2 case, what is the equation of IDM2? That is my I naught 2 e to the power q VGS2 by eta kt. And what is my I naught 1? I naught 1, sorry, IDM1. So that is I naught 1 e to the power q VGS by eta kt, where I naught 1 and I naught 2 is also proportional to your WIL parameter. Okay. So now now what I did like I need VGS2 and VGS1, because at the end I need VPTAT. So my VPTAT is VGS1 minus VGS2. So I need VGS1 and VGS2 value. So here it is my VGS2 value and here is my VGS1 value. And VPTAT del V equal to VGS1 minus VGS2. So that is my eta kt by q ln I naught by I1. And this I naught 2 by I1, which actually proportional to my like like W by L ratio of M2 and M1 as well. So here it is my ln k. So basically del V is equal to L eta kt by q ln k. So if I so we can clearly see that our circuit is like voltage generation is totally dependent on temperature, that is T here, and the it not depends on my I bias. So entire circuit you never seen the I bias also came or dependent, like your voltage is dependent on I bias. Okay, so this is the temperature variant circuit. So basically this is the derivation part and the application part at the end. So higher this circuit is used required. So basically obviously temperature sensor, so measured and monitor temperature in integrated circuit basically, and band gap reference generator, voltage regulator, thermal protection circuit, shutdown system at a critical temperature. So basically here are the some application, and mainly where you design a chip, so you entirely like in most of the part in your chip area there you can provide this circuit, and you can check that uh, uh, if there are any like your temperature is huge or not. So it detects the temperature like on a particular chip area. If the temperature is increased maybe more than its like uh, sustainable rate, so otherwise your chip will be damaged. So that's for reason this circuit will entirely chip it is used. Okay, so that's all.